Today's my topic is state-based model, Kalman filter, and smoother. And our whole tutorial will be divided into 5 parts. The first one, it will give a brief introduction of the state-based model. And then we will talk about 2 algorithms that are related to state-based model, the Kalman filter and Kalman smoother. Then we will come to how to learn the parameters inside this state-based model. Because as we all know, when we define a model, there are some parameters that have to be fixed. So this one will tell you how to learn it automatically instead of fix it. And finally, we will talk about its applications in finance. So let's begin. At first, let's talk about the introductions of state-based model. We will give you a brief introduction here. This is a simple example. When you consider a car is driving along one axis, which is called z-axis. And then the real positions of the car is often hidden from us, which is called hidden state. And its hidden state at time t is denoted as jt. What's the meanings of hidden state? When you imagine when you're in a stock, then whether the stock is bull market or not, it itself is a hidden state. Hidden state means some information that you don't know, you don't really figure out or observe. And consider a car has an odometer showing that the car is driving at a constant speed u. And because this odometer, which is the measures of the velocity of the car, it is like a panel, and it will bring in a process noise, which denoted as WT. And then the hidden state will have this equation. The position of the car at time t is the position of at t minus 1 plus the velocity multiplied by the time period, and also add up a Gaussian noise. So using this equation, we can make a prediction at t minus 1 on the location at t. For example, now the car is here, we can make a prediction of our car at t, and it will look like a bell because it follows a Gaussian distribution. And so this is describing how the car is driving along an axis. And then simultaneously, we have a GPS, which is a sensor. It will observe the car's position. And its observation is denoted as x. So you should make a distinction between x and z. Z is its real position, but x is the observation. These observations also has a noise. For example, there are 5 meters noise and so on. So the observation equation will be look like this one, which means our observation is in fact the real position plus a Gaussian noise. So in this graph, you can see that this one is the prediction and this one is the observation. They may not be the same. And the problem comes up, how to find out the real position of the car. We don't know exactly the real position, but we have the prediction and the observation. And in this case, we can simply integrate them together, integrate these two distribution together and put more weight on the one with lower uncertainty. You see, this one, the Gaussian has a lower uncertainty. This one will have a higher uncertainty. So we will trust more in the prediction instead of the observation. So in fact, this is the ideas of Kalman filter, and we will talk about it later. So these pictures you should bear in mind. Yeah, let's continue. In the previous example, we write up 2 equations, which is called state equation and the observation equation. And we put it together. As you can see, it's a really elegant form. And we can also draw it out like this graph. As you can see, the state, which is the hidden location, or the real location of the car, is in fact follows a chain. Each node is only dependent on its previous node, but not on the nodes that is before. So it is in fact follow a Markov property. And each observations will only depends on this relevant states, relevant hidden states. So this is how we illustrate this equation. And more generally, a state-based model will consist of a transition matrix or an observation matrix, which try to map the state space into the observed space. The two space can be different. What you observe can be something like acceleration or is latitude or something like that, but they don't exactly to be the position of the car. So there is a linear transformation here. And the state can be, there are multiple space, so multiple states. So it can be a vector. The observation can also be a vector, meaning that there are multiple sensors recording the position at the same time. And so this is a more general form, nothing special compared with previous one. And its graph will look like also almost the same, but with a matrix here. The A here means the state transition has a linear combination relationship, and the C here will also has a relationship, projection relationship. And from this graph, we want to highlight that the hidden state follow a Markov property. And what's the benefit? The benefit is that when we want to write down the joint distribution of the state and the observation, we can simply write down like this. The distributions of the initial state multiplied by the cross products of how the state transit, and also multiplied by how the observations occurs. So this is a really elegant form of the probability. And so before we go to the common filter and common smoother, I want to clarify three concepts here. The first one is called prediction. Assumes that we have already observed t-1 observations. And then when we want to predict the state at t, it is called prediction, or predict the state that in the future, like t+1, t+2, this is called prediction. And filtering means after we have observed this t-1, we try to update our current states, our state t-1. Because in previously we have predict one, but because after we have observed the new observation, we can try to correct its prediction. This is called filtering. And smoothing means we try to update previous estimation of the state. So these are three concepts. So filtering and prediction, when they combine them together, it will brings in what we call a forward algorithm, a forward flow. Forward means each time we first predict, for example, we first predict, and then after we observe xt, we try to filter it, and this is called forward. We are always looking forward, and so this is the concept of common filter. And the smoothing is achieved by using common smoother. It's trying to do the backward flow. And so let's get in the details of common filter. Common filter is first designed by the guy Kalman and also a Russian physicist. And it was first applied in the Apollo project. And they are used to track the manned spacecraft. And nowadays it's widely used in many areas like the control system, the computer vision system. And I think for our students, more importantly, it's quite useful in the time series forecasting. And with this state-based model, we can forecast the price, we can forecast the volatility, we can forecast the trading volume, as we will see in later chapter. And so this is the backgrounds of common filter. And common filter is simply composed of two components. First one is called prediction, and the second one is correction, as we have shown previously. Prediction means at time t-1, we will try to predict the state at t. So this is the denotion of this estimation. JT means our estimations of the state at t. conditions on t-1 observations. And we will also provide the uncertainty in the prediction, which is the variance of our Gaussian function. And the next step is called correction. Correction means after we have observed xt, the observations at time t, we will correct our state. We will correct this because we have estimated this one. And we want to correct it. And it would have a denotation like this, which means our corrected state at time t conditioned on all t observations. And we will also try to update our prediction uncertainty, denoted as this one. And let's see how it works in our previous example. Our previous example, the state-based model is placed here. And we have a previous correction. Assume at t-1 we have a previous correction. The first step of Kalman filter is doing prediction. We will predict what the car's position look like in the next time step at time t. So this will be a bell. And then we observe at time t, we observe from the sensors. So we will have another bell. So the problem, as you can see, this one, is variance or its uncertainty is defined as this. And the observation, we have the observation noise defined as R. So the problem is that how we do the correction to find out the real position. So intuitively, with these two Gaussian, we'll do the correction is by simply multiply these two Gaussian PDF or Gaussian function together. You might think, okay, it is so heuristic, but in fact, there is a proof by using Bayes' rule to prove that this one is valid. So try to remember that the correction is in fact the corrected Gaussian is in fact the multiplication or the products of the prediction and the observation. And so let's go into details of this multiplication. As you can see, the expected value of our correction is in fact a weight sum of the expected value in the prediction and the expected value in the observation. And their weight is controlled by KT. And we will see KT is in fact the common gain, a really important concept in Kalman filter. And as for the variance, it has this relationship. So how is this common gain defined? Common gain is defined as the uncertainty in the prediction. We have noticed that this one is called uncertainty in the prediction because it's t conditions on t-1, it is doing prediction. This is uncertainty in prediction, and this is the uncertainty in both the prediction and the observation. So this is the ratio. It relates between 0 and 1. What's the meanings of this common gain? As you can see, the common gain means how it gives us the information of how much we should trust in the prediction or how much we should trust in the observation. A simple example, when we have a really strong prediction, which means the uncertainty in the prediction is pretty small, and a very noisy sensor, the uncertainty in observation is pretty large, then this common gain will become pretty small. As when we look back, if the common gain is pretty small, our correction will mainly lay on the prediction, but forget about the observation. So you can see the effect. It's like a switch. And so when we sum up these algorithms, prediction, correction, and it's quite simple, just few lines. In the line 2 and 3, they are doing a prediction. Predict states, predict uncertainty, and 4, 5, 6 are for the correction. First, we have to compute how much we should trust in the prediction or how much we trust in the observation. And then we will do the correction. We would correct the state and correct the uncertainty. And then this will become a loop, and we will just go forward. And this is the intuitions of the Kalman filter. Let's have a look at this experiment. Consider that it's the same as the previous example, but now we have some settings. Consider that GPS, our observation, has a smaller error than the odometer in the state equation. GPS is more reliable. However, during this gray area, the car is driving through a tunnel, and so the GPS error drastically increased. So well, as you can see from the plot, at the beginning, I should clarify first. The red one is the real state or the real location of the car, which is hidden from us. We cannot see it. It is just generate. It's a synthetic data, but we don't really know. In fact, we cannot see it. And what we can only see is the green line is from the GPS, is the observation from the GPS. And as you can see, when we trust, at first we pretty trust in the GPS. So our blue line, the result of the Kalman filter, is almost the same. It follows the trains of the GPS. But when the car drives in the tunnel, we will forget about the GPS. We will follow the state transition. We will follow our prediction. We will not believe in observation anymore. And so the Kalman filter will go this way. But when it go out of the tunnel, we will try to believe in the GPS. So as you can see, the result of the blue line, the Kalman filter, has a really great approximations of the real position. So this is the powers of Kalman filter. A more general algorithms designed for the general state-based model is almost the same. 2, 3 for prediction, 5 or 6 for correction. Yeah, you don't have to get into the details. And so in summary, what is the pros and cons of the Kalman filter? The advantage is that the Kalman filter based on state-based model, and the state-based model allow noise in initial estimate, in state transition, and also observations. So it is a really well-designed model, and you can use in many cases. And Kalman filter is the optimal solutions of this model. And the second advantage is that it doesn't require to store any historical data, because when we do a forward, when we're doing the forward loop, a forward flow, we only need to update our previous state and then predict, and then update, predict. We don't have to store our previous states because of the Markov property in the hidden state. So the third advantage is that it is computationally efficient. It's pretty fast, just few lines and forgot about the previous data. So it's widely used in real-time application. For example, our self-driving car nowadays is pretty popular. And the cons of the Kalman filter, or we call it the limitations of the Kalman filter, is that it is designed for linear Gaussian state-based model. But in practice, the noise may not be Gaussian, and the state transition may not be linear. So the traditional Kalman filter is limited. Well, people have developed some variants to cope with this kind of problems. For example, the extended Kalman filter, the unscented one, and particle filters, and it's also a good choice. So this is all about Kalman filter. In the third part, we will go into the Kalman smoother. Before we get into the details, and actually we will not talk about the detail because it's quite complicated. We should refresh our concept. What is smoother? Smoother is to trying to get a better estimations of the state previously after we have this observation. So when we should apply it? Consider if you're in a hedge fund, or you have a historical data of the previous year, the whole year, and you want to find out the hidden information in the previous year. And so in this case, you are doing analysis. You are not doing prediction. You try to analyze the performance of the previous year. And then this is the case when Kalman smoother comes in. If you try to help you to find out all the hidden information previously based on the whole year data. So here, here I will give you the same example as before, the car driving through a tunnel. But right now, I will show you the performance of the smoother. The red one is still the real position. The green one is the Kalman filter. And the blue one is the Kalman smoother. As you can see from this case, the Kalman smoother will provide a much smoother performance than the filter. And for example, here the filter suffers from a downward trend, which is not what we like. But in the smoother, we have already solved this problem. It becomes smooth and provide a better approximation. And so, generally speaking, the Kalman smoother can be written like this, and it is a backward flow algorithm. But before we run the Kalman smoother, we have to do the forward first. So, Kalman filter is always before the Kalman smoother. You don't have to get into the details of this equation. And in the fourth topic, in the previous case, the Kalman filter and smoother, we assume that we have already know the parameters. What is parameter? Parameters is just when you are doing a portfolio design, portfolio optimization. You already know the parameters mu, parameter sigma, but in practice, you don't know, you may not know. You have to use some tricks to train them, to find them. And this is called learning. And we have to learn, for example, in this state-based model, there are some parameters. The A is a parameters, the transition. But perhaps in reality, we don't know the transition. But although in our first example, we know that, okay, the transition A will be 1, but in fact, we don't know in some cases, in most cases. And we may not know the noise, the covariance of the noise, we may not know that. So we require to study these parameters from our training data to help us to build a complete state-based model. And these parameters can also be time varying. And so the problem is how we try to learn them, how we learn them. When we start off our learning theory, the most important one is called the maximum likelihood estimation, which means we're trying to maximize the data log likelihood. It is written in the following form. And as we can see, our objective is the data log likelihood, the data likelihood. And in practice, we don't know the probability of the data. We only know the probability of the join of the hidden state and the observations. So we have to take the integral to get this px. Forget about the log. Yeah. And the problem is that this integral is pretty difficult to calculate. So this may not be a good choice. We may not directly maximize this data log likelihood to find out our parameters. So alternatively, if we know the hidden states, we can try to directly maximize pxj, the join probability, because this has a really elegant form, as you can see here. Well, the problem is that in practice, we don't know the hidden states. So how we can find out the parameters? This is when the expectation maximization algorithm comes. In this case, we don't know the j, but we can calculate the expect value of the j. We may guess a j. So this EM algorithm is doing like this. EM algorithm, expectation maximization. Expectation step, it has 2 steps. One step is expectation step. It will calculate the posterior distributions of the latent state, denoted as PJ conditions on X. So what's the meaning? It means that we have these observations, we can predict the state, or we have a guess of the J. And then we can, if we have already guessed the J, we can calculate this log likelihood, the objective of our MLE. And in the M step, it's just directly maximize this expectation. In most cases, this maximization step is pretty simple. It always has a closed form solutions. But the problem is that how we can find out the posterior distribution, how we can guess the state from all the observations. In fact, we have already done that. With the Kalman filter and Kalman smoother, we can calculate the expect value of the states. Because as previous chapters, we have talked much about how we can guess the state from our observations. This is when it comes in the learning theory. So the EM algorithm can be summarized as the following. We first have an initial guess of the parameters. Then in the E step, we use the Kalman filter and spoofer to calculate their probability, their posterior probability. And then we can calculate the expectation of the complete data log likelihood, our objective function. And then in the M step, we will optimize it. And we don't have to use CVX to do that because it has a closed form solution. And we can simply write it out. So it's pretty simple. And these new estimate parameters will feedback because the initial guess of the parameters may be pretty worse, and we have to loop to find out whether there are better estimation of the parameters, and finally, all the parameters will converge. So this is the ideas of EM algorithm. And till now, we have already learned Kalman filter, Kalman smoother, and how we learn the parameters. All these have already been coded or packaged in a package. For example, in R there is a package called MARS, and it can support a really easy implementation. It has a clean interface. If we want to use this state-based model, you can just simply define it, and they will train it for you, and they can do the Kalman filter and smoother for you, and you don't have to worry about your coding. So it's pretty easy to implement. And finally, we will talk about how this state-based model applies in finance. One application I want to share today is the intraday trading volume decomposition. Trading volume, I think most of you have already noticed. And trading volume is showing how active your market is. And intraday here means within each day, we don't only have one trading volume. We have sampled it. Every 15 minutes, we have a record of the trading volume. And so as you can see here, this is one day, this is the second day. And the trading volume is look like, it goes, because at the beginnings of our trading hours, the trading volume is pretty high. And then it will drop down. And later at the end of the trading hours, it might achieve a peak, which is in line with our intuition. And this is called a smiley patterns or U-shaped pattern. And we want to decompose it. We want to decompose it in several components. Volume decompose it in an additive. The first one is the daily component. Daily component, which is a lower frequency component, which represents the daily average of the volume. Each day we have a daily component, and the next day we have a next daily component. So T here denotes day. And within day, we have many beans. We have many samples. The I will range from 1 to maybe 20. There are 20 samples each day. And I denotes the index of the bean. So daily doesn't care about what is the index of the bean. All the beans have the same daily component. But for the periodic component, it cares about the bean, because when you in different times in a day, then the periodic term may be different. So this is aimed to reproduce the time of day pattern, the smiley pattern, the U-shaped pattern. This is coded in the periodic term. There is another noise term. And so we can construct a state-based model based on these assumption. For example, here, this is one realization. And each moment in the state model denotes one day. This is one day, this is the second day. One day transit to the second day. And in each day, there are many hidden states. The first one is the daily hidden state. Each day has a one daily term. And they have n here denotes the numbers of beans. They have n periodic terms or periodic states. So here will be n plus one hidden state. And it will transit to another day. How we do it? Alpha is a parameter we want to learn. We want to find out whether the daily components will change. What is their ratio? But for the periodic term, which is you can see here is the identity matrix. Each periodic term for each bean, we hope that it look the same because it is one. We want it to stay the same. But here we allow some noise, and definitely it can change a little bit, but not a huge change. So this is the meanings of this state equation. And for the observation, it means each volume is a combination of daily and a periodic term, because as we can see here from the additive model, daily plus a periodic. So here each volume is a daily plus one periodic. This is a diagonal matrix. And this is the way we construct a state-based model. How it performs, you can see the result. For the log volume, the volume, we plot here. Now, after running the Kalman filter and smoother, we can get the decomposed result, the daily term, the seasonal term, and the residual term, which is we think it is the noise. In the daily term, you can see it is like stairs, and it is what we want. It depicts the daily average of the volume. And season, you can see seasonal term, it looks like the smile face or W shape, U shape, doesn't matter. And we can find out this hidden information from looking in this really noisy signal. We can extract two really important hidden information by construct a state space model. And in the residual, the noise, we hoped it to look like a white noise. And yeah, it's pretty noisy and nothing, not many valuable informations can be found here. So this is the powers of Kalman filter and smoother. So, okay, one thing. Although we want to, this is designed for decomposition, but as we can see, we can do a time series forecasting. How do we do forecasting in this example? We have, I believe that we have already in our homework, we have done something similar. We try to decompose a signal, and then we like to predict the trends of each component. For example, this one is when we fit AIMA models on it, it will look like so we can predict the future daily term, how it looks like in the future. And the seasonal term, we can keep it the same. This month phase, this month phase, this month phase. So the predictions of the future trading volume can by simply add up these two terms together and set the noise to be 0. And the results have already shown that using this method outperform all of the other methods in trading volume prediction. So this is the powers of state-based model. So, and I think this is the all of today's tutorial, and I will give you a conclusion. The first is that we talk about the state-based model. It is consists of a marker chain or marker hidden state that follow marker properties, and then plus an observation model, which is how we observe from the state. And inference in the state-based model or the forward algorithm is called the Kalman filter. And the backward one, so the smoothing one, is called the Kalman smoother. And the EM algorithm help us to learn the parameters efficiently. And the state-based model from our application, we can see that it's quite useful in finding out the hidden information. So when you want to use these state-based models in other financial applications, it's pretty simple. You can construct a state-based model, or perhaps you don't know which state you want, you can just put, you can have a try, put some state. You may not know how the transition of the state from t-1 to t, how to transit. You can set it as a parameter, and you can learn it with EM algorithm. And and in this way, you can find out the hidden informations in some observation. For example, you observe the price, and while this method, you can find out something below the price, something more than the price. For example, whether some trading patterns inside it, whether it is a bull market or so on. So this is the powers of state-based model. And if you want, you can go deeper in these links, and you can find out more information in Kalman Filter. So thank you for your listening.
Okay, thank you very much, Shengjie. Anybody has any question for him? I want to say that the Kalman filtering is really a very useful technique, very versatile. It can be applied in virtually any area. Initially, it was proposed for ballistic purposes, right? To control the position of missiles and planes, spaceships. Many years ago, in the early 60s. In the early 60s, so we are talking about, a long time ago, and more than half a century ago. But now it's used in every area. And of course, in finance, it has many applications. So Shengjie has shown you just one application in finance, right? For the volume modeling, but it has many other applications. Definitely, it's a bit sophisticated for the scope of this course. This is an undergraduate course, so it's too much for this course. But at least it's good to know that something like this exists, right? It's good for you to know this. Anyway, if there are no questions, then we can stop here. Any question?
Then I guess since like you mentioned this method was developed in like the 1960s, then has there been like newer methods that have been developed? Like,
Shengjie, you wanna reply to this?
In fact, the Kalman filter, we have shown that before there are some variants to deal with different kinds of problems, as we have go to the Kalman filter. Oh, sorry. And the Kalman filter is designed for the easier case, and in practice, your models may be more complicated, and so you can use some other variants of the Kalman filter we have shown here. And I know that you mentioned the Kalman filter is designed in 1960, but definitely there will be something new, but it's nothing about Kalman filter, because Kalman filter is one optimal solutions of the state-based model. So you mentioned that there may be some model that replace state-based model. This is possible, and there are definitely some other models to try to model the world in different ways. But for the Kalman filter itself, Kalman filter is the optimal solutions of the state-based model. So you cannot find a better solutions of the state-based model, in the literature.
So let me repeat just to clarify what you have just said. But basically, the Kalman filter is the optimal solution in a very particular case. So the transition functions have to be linear. That's very, very specific. And the noise has to be Gaussian.
Yeah.
That's very specific. So for that case, yes, it was known since the 60s. But of course, many applications do not fit into that framework, right? So what do? Well, he has listed here the extended Kalman filter. That's for the general case, right? Nonlinear functions, noise, and the uncentered Kalman filter. But what people are using now is what's called the particle filtering methods. That's when the model is so complicated, so general, that there's no way you can do anything analytically. You cannot solve any integral because you know, in this you need to solve some integrals. So if the model is complicated, you cannot solve those integrals analytically. Forget about it. So you need to resort to very heavy computational methods, Monte Carlo computational methods, and that's in particle filtering. And this is something you can only do with the current computers that we have now. Before, in the past, you couldn't even dream of doing that. So that's what people are doing now, these particle filtering things. But computationally, it's demanding, yeah. Any other question? But it's a fascinating topic, really, this Kalman filtering. Okay, time to finish. So again, thank you, Shengjie, for this nice